Okay, so one of our topics for this week is analyzing categorical data. And for categorical data, we use something called ChiSquared distribution. Looks something like that script X with the squared symbol on it. And there's actually a couple of different types of chi-squared analysis. There's the goodness of fit mentioned here, and then there's a test for independence. So suppose that we want to determine if the proportion of the different colors in a large bag of M&M candies matches the proportion that the company claims is in their candies. So we can record the color of each candy in the bag. This would be univariate categorical data. So only one variable, and it's split into categories. We're looking at the frequency of categories. So how many categories would there be? Well, it depends on how many colors they claim to use. In this case, there are 6 different colors. So there are 6 categories. So we say K equals 6. That's our number of categories. We could count how many candies of each color are in the bag. So we'd open up the bag, tear it open, and count each color. And let's say in this bag we get 23 red, 28 blue, and on down the line there. This is called a one-way frequency table. So we have one variable, the color, and each of their frequencies. A goodness of fit test is taking a purported, claimed percentage for each category and comparing them to the observed percentages, observed frequencies. So our null hypothesis is always whatever the claim that's being made. So the goodness of fit test is used to analyze this, and our claim is just whatever they say that the proportions are supposed to be. So P1 is whatever the hypothesized proportion for that first category is, P2 is whatever the hypothesized proportion for the second category, on up through PK, which is the last category. Then HA, the alternative hypothesis, is basically saying that the null is not true. In other words, a lot of times it's written as at least one of those proportions is different. Our test statistic is going to be the sum of, that's our chi-squared there, is the sum of, for each cell, each item in the table, the observed count minus the expected count. We square that difference, and then we divide it by the expected count. The chi-squared value is always positive. These will always add up. Notice the squared here means that that difference is always going to be a positive difference. So we will always reject if our test statistic is larger than a critical value of chi-squared. So p-values, a little bit more difficult to do. The calculator isn't a great tool for the p-values here. It's just the probability of getting a larger test statistic underneath the conditions. In this case, degrees of freedom of k minus 1, and so on. So our assumptions, the observed cells are based on a random sample. So taking that bag, that would be a random sample of, as long as it's chosen at random and no system is involved. And the sample size is large. It's enough so that we can reasonably expect each cell to have a count of at least 5. If we get counts in those cells of less than 5, then it's not really a valid test. So facts about the chi-squared distribution. It is kind of bell-shaped, but it is skewed. And it is different for the numbers of degrees of freedom. For 3 degrees of freedom, it's not much more than half of the bell curve. And it's always skewed to the right. But notice as the degrees of freedom gets larger, it does start to stretch out and becomes a little bit more like the bell curve. So a common urban legend is that more babies than expected are born during certain phases of the lunar cycle, especially near the full moon. So the table below shows the number of days in the 8 lunar phases with the number of births in each phase for the 24 lunar cycle. So there are 8 phases, so k equals 8. Our hypothesis, or proportions here, P1 is the proportions of birth that occur during the new moon, P2 is the burst during the waxing crescent moon, and on down the line all the way down to the waning crescent moon. There is a total of 699 days in the 24 lunar cycles. If there is no relationship between the number of births and the lunar phase, then the expected proportions equal the number of days in each phase out of the total number of days. So what we're saying is the number of days in each of these phases divided by the 699 total days in the 24 lunar cycle. So that gives us those proportions. The proportions of births should be the same. So our null hypothesis is that the P1, the proportions of births during the new moon, is 0.0343 because that's the proportion of the time of the cycle that is in new moon, the phase of the new moon, and again down the line. The alternative is, this book just says that the null hypothesis is not true. Most textbooks will say just that at least one of those proportions is different from what the null hypothesis is. So there are a total of 222,784 births in this sample. If there is no relationship between the number of births and the lunar phase, then the expected counts for each category should equal the total n times the hypothesized proportion, just n times p. So the observed number of births for the new moon was 7,680. If we did the n total, the 299,000 times P1, the 0.0343, we would get 7,641.49. That's actually not too far off from the 7,680. And we do that for each of them. And looking through them, you can see that they're actually relatively close. There's not a huge difference in them. But is that difference, the little bit of a difference we see, large enough to be a significant difference? So our test statistic for each item, notice that for the new moon, 7,680 was the observed births, 7,641.49, that was the births calculated as our expected number based on the proportions. We subtract, we square that difference, and we divide by that expected amount again. That gives us the portion, that contribution of that phase of the moon to our test statistic. And we have one of those terms for each of those 8 phases of the moon. We add them all up in this case, we get 6.557. Now I should show you that calculation here quick. So what we would do is we do parentheses here, 7,680 minus 7,641.46, close the parentheses, x squared divided by that expected value, 7,641.46. I should put 49, I should put in there. Now you have 0.1944 about. Let me redo that. I had put 0.46 in the top there. It should have been 0.45. So 7,680 minus 7,641.49, not 46. X squared divided by 7,641.49. We're going to get the same proportion pretty much, a little bit different actually. 0.1941 is what we get. That actually is a proportion. That is the contribution of this term. So the new moon phase to our test statistic. Now we did that for all 8 phases and add them up. And that's where we got that value of our test statistic of the 0.6557 or 6.557. So again, we went through all that and we got that 6.557 as our test statistic. For a p-value, this case we need to know where it's at. We didn't really define our p-value yet. But we have 7 degrees of freedom because k was 8. Oops, I turned off my pen. So since k was 8, k minus 1 gave us 7 degrees of freedom. The alpha that we used here was 0.05. Our p-value we find by looking in the table, and we find the test statistic for 7 degrees of freedom, the one that is closest to the point, the 6.557, without going over. So if we have the one we find is going to be a little bit smaller than that, and that in the table corresponds to a p-value of 0.10. So we know that if the test statistic is greater, the p-value is also greater. So that tells us our p-value is at least 0.10. The x-squared test statistic is smaller than the smallest entry in the degrees of freedom for equals 7 column in our appendix table. So because it's smaller than that, that smallest value is for 0.10. So the p-value has to be larger than 0.10. So since our p-value is greater than alpha, we fail to reject H0. There is not sufficient evidence to conclude that the lunar phases and the number of bursts are related. So what type of error could we have potentially made with this decision? Well, we failed to reject the null hypothesis. So that means it would have been a possible type 2 error. They really are different, but we failed to reject. A study was conducted to determine if collegiate soccer players had an increased risk of concussion over other athletes or students. So here we're going to do a two-way frequency table. So this is going to be what they call a test for independence. It's very similar. The expected values are a little bit trickier to find. So it displays the number of previous concussions for students in independently selected random samples of 91 soccer players and 99 non-soccer players and 53 non-athletes. So here we have two different categories. Their participation in athletics and their number of concussions that they've had. So we make this two-way table is called the contingency table. We've used those before. So top is univariate categorical data, but there are several categories, several different independent samples. Soccer players, non-soccer players, and non-athletes. So it's like 3 of those univariate tables put together. So the green numbers there are what we call the observed counts. Those are the values that we actually found when we surveyed those players. In the blue, those are the totals. They're called the marginal totals. In probability, we refer to them as the marginal probabilities. So these are the row totals. This is all the total soccer players, total non-soccer players, and total non-athletes. This is the total of 0 concussions, 1 concussion, 2, and so on. The red here is the grand total. So there's a total of 240 people in this table, period. So if there were no difference between these 3 populations in regards to the number of concussions, how many soccer players would you expect to have no concussions? Well, there's 91 soccer players out of 240 total. So we would expect the proportion of people with 0 concussions to be the same as the proportion of the soccer players out of the total. So there's 158 out of the 240. That's the proportion of people that have 0 concussions. So we'd expect that same proportion out of the 91 soccer players. So that would give us the expected value for the number of concussions we would expect, or number of soccer players we would expect to have 0 concussions. So our null hypothesis is that these two, well, what we're going to perform here is a chi-squared test for homogeneity. That's used to analyze univariate categorical data from 2 or more independent samples. Sometimes this is referred to as a test of independence. So the true category proportions are the same for all the populations or treatment. That's always our null hypothesis. So the alternative hypothesis, the true category proportions are not all the same for all the populations or treatments. So in other words, the variables are not independent. Our test statistic is the same as it was for the univariate. It's the observed minus the expected. We square that difference and then divide the square by the expected amount. And we add those all up. So if we assume that they're independent, we assume that those frequencies are the same. The proportions are the same. It's the row total, the column times the column total divided by the grand total gives us the expected value. The p-value then has to be looked up in that table. Our degrees of freedom is the number of rows minus 1 times the number of columns minus 1. So this is a 3x4 table. There are 3 rows, soccer players, non-soccer players, and non-athletes. And there are 4 columns, 0 concussion, 1 concussion, 2, and 3 or more. So this would be a 2 times 3 or 6 degrees of freedom. So we would look up 6 degrees of freedom and we would have to use the appropriate alpha value to find our critical value. Our assumptions: data are independently chosen from independently chosen random samples or from subjects who were assigned at random to those treatments. The sample size is large. All expected cell counts to be at least 5, and that is true. If they're less than 5, rows or columns of the table may be combined to achieve this. So we can combine categories if we have to. So in this table, the non-athletes, there's only 3 and there's only 0 there. So that might be an issue for us. So for the null hypothesis, proportions in each response category, number of concussions are the same for each of the 3 groups. And for the alternative, category proportions are not the same for the 3 groups. So we find the degrees of freedom here. We ignore the totals. Like we said, there's 3 rows and 4 columns. So 3 minus 1 is 2, 4 minus 1 is 3. So 2 times 3 makes 6 degrees of freedom. Another way to find this is you could cover 1 row and 1 column and count how many cells there are. So then we calculate the expected count. This 59.9, remember that comes from the row total, 91, times the column total of 158 divided by the grand total of 240. And that's where we get each of those expected values. Notice that not all the expected counts are at least 5. So we're going to combine the column for 2 concussions and the ones for 3 or more. So we redo our frequency table, and then we have to go back and recalculate our expected values. And now we see that all the expected values are more than 5. Notice the observed value being less than 5 doesn't matter. It's the expected values that all have to be more than 5. So now this is a 3x3 table. So 2 times 2, 3 minus 1 times 3 minus 1 gives us 4 degrees of freedom. Our test statistic for each cell, we did the observed minus the expected, squared it, and then divide it by the expected. We add that up for each of those 9 cells to get a test statistic of 20.6. The p-value of 20.6, if we look it up in our table, well, it is to the point where it's smaller than the smallest number, so that means it is, or larger than the largest number. So its p-value has to be less than 0.001, which of course is less than alpha of 0.05, so we will reject the null hypothesis. And the proportion of concussions is different depending on whether you play soccer or not. Now, we can't really say if the soccer players are the ones that are different. All we can really say here is that the 3 groups are not the same proportion of concussions. Now we can look at the chi-squared contributions, to see which of the cells has the greatest contribution, which ones have the biggest difference between the observed and expected. But also remember, a large expected value, we have to divide by the expected value, so that can make a difference as well. So our chi-squared test for independence, slightly different than the test for homogeneity. The last one, the test for homogeneity, we weren't saying that we were saying the 2 variables were independent, but what we were really saying was that the division of categories is the same for each of the 3 different samples. Here we're saying that one variable does not have an effect on the other variables. Very, very tiny difference, but it's slight. The test independence and the test homogeneity go through the same process, so it really doesn't matter if you can precisely pick between which one is which, because you're going to handle the data the same way, come to the same conclusions either way. So our null hypothesis will always be that the two variables are independent. So the alternative is that they're not independent. Our test statistic is exactly the same as it was for the other tests. So to find our expected counts, we do the same thing, row total times column total divided by the grand total. And our p-value is found exactly the same way, number of rows minus 1, number of columns minus 1 to get the degrees of freedom, and we look it up in that table. Our assumptions, again, is that this is randomly selected data and that the expected values of each cell is at least 5. So what we're looking at here is body piercings and tattoos based on what year they are in college. We want to see if there is a difference in those proportions. It would make sense that people that were later on in college would have more piercings and tattoos just because they've had more years to accumulate them. But let's take a difference. Or let's take a look and see if we can find that difference. So the null hypothesis is that the class standing and body art are independent. The alternative is they're not independent. So if we assume that the null is true, what would those expected values be? We have to find those row totals and column totals. Remember, it's row total times column total divided by the grand total. And we get the expected value for each cell. So now this is a 4x4 table. There are 16 cells, so we have to do each of those 16 components towards our test statistic. 4x4, so degrees of freedom are 4 minus 1 times 4 minus 1 is 3 times 3 is 9 degrees of freedom. Our test statistic, again, it's the observed minus the expected. We square that and then divide by the expected. We do that for each of the 16 cells and we add them up to get 29.48. Looking at our table, for 9 degrees of freedom, 29.48 has a p-value of less than 0.001. We were using an alpha of 0.01 here. Well, 0.001 is definitely less than that, so we reject HO. There's sufficient evidence to suggest that these two are not independent. And like we mentioned, it makes sense that the older you get, the more time you've had to accumulate more tattoos. Again, which cells contribute the most to our chi-squared statistic? Well, the 23 and the 12.7 are the ones that are the furthest apart, so that is our biggest contributor. So that would be the group that seems to be the most different from the rest. So that is chi-squared test. We'll come back and do a ANOVA test in just a little bit.